Arcing, electricity flowing through space. We see it in nature as lightning. In our electrical transmission systems, it can be a serious problem. Tracking, or flashover. This electrical discharge follows the path of damaged insulation. Hundreds of years ago, when sailors observed a bluish glow in the night sky, they called it St. Elmo's fire. We now know this phenomenon results from the ionization of air around a conductor of electricity, and we call it corona. These electrical discharges can mean energy loss. They can cause radio and television interference. They can cause equipment breakdown. Their effects can sometimes be dramatic. It is important to know when and where electrical discharge occurs as part of an effective program of preventive maintenance. Ultrasound technology allows high-voltage equipment to be scanned and sources of electrical leakage located without costly shutdowns. As a complement to other technologies, its usefulness has a wide range of applications in locating electric arcing, corona, and tracking. You'll see how ultrasound technology is used to test a wide range of electrical equipment. In theory, we can test any equipment for arcing, tracking, and corona. However, most applications tend to be in the high voltage range. To clarify what we mean by low, mid, and high voltages, we'll use these generic voltage definitions. Low voltage is less than 1,000 volts. Medium voltage refers to the range between 1,000 and 100,000 volts. And high voltage means anything over 100,000 volts. In order to show functional applications, we'll go on-site to power plants, substations, and user facilities. Let's start by learning to identify a destructive electrical discharge. But before we do, a word of caution. Always think in terms of safety. Always follow your company's or plant's safety guidelines when working around electrical apparatus. Normally, electrical equipment should be silent. If you hear sounds, they may be a constant 60-cycle hum or steady mechanical noises. These will not be confused with the erratic, sizzling sounds of electrical discharge. What you're listening for sounds like a frying egg, uneven and poppy. However, not all electrical discharge is destructive. Non-destructive or nuisance corona may result if there are sharp points or edges on the conductors of high-voltage lines. Electrons may jump off these points, especially in humid weather. Similarly, insulators that have cracked or broken bells may have surface tracking over the broken areas and corona from the sharp edges. This may not be a serious problem. It may be explained by sharp edges, burrs, or pointers at the ends of the insulators, which can give off a nuisance electron spray. Using ultrasound, we're able to distinguish between these sounds. An intermittent sound indicates destructive corona. A continuous sound indicates nuisance corona. Experience and familiarity with your equipment will make diagnosing problems easier. Due to the nature of the phenomenon, there are no exact standards to predict what meter readings will indicate whether you are experiencing real or nuisance corona. The best testing method is to compare the sound quality of areas of similar material and function. Listen for differences as you visually inspect them and make notes for future comparisons. Just as you may use complementary technologies, you may use your own senses to detect changes in your equipment. You may be able to smell ozone or see discoloration, for example. Monitor your equipment regularly by listening to everything and record the results. Although the log mode is used to record in real time when scanning to pinpoint a problem site, we recommend switching to the LIN mode for a steady response for monitoring purposes. This will also allow for noting decibel differences. In the LIN scale, every change of 20 increments on the meter is approximately 3 decibels. Note whether you heard arcing, tracking, or corona, and include the location. Also make note of the temperature and relative humidity at the time of testing. You'll find weather conditions affect the results and should be taken into consideration when making comparisons. As an example, high humidity or rain will allow for greater arcing, tracking, or corona. With experience, you learn to detect changes, know when further investigation is required, and recognize a gradually worsening condition. However, you won't hear any real indicators relative to time for destructive corona. The time to correct the problem is immediately. An explosion may happen sooner or it may happen later, but it can happen at any time and without warning. This is the actual sound of destructive high-voltage corona at a severe stage. Listen to this sizzling sound. This is the sound of tracking over the surface of a cracked insulator. Whereas corona is found at points where electrons jump off into the air, with tracking you'll be able to follow the sound of the electrons running along a damaged site. We use the ultraprobe to scan cables operating at high voltages, so safety is a major concern. Never violate the integrity of metal-clad switchgear. If you are ever in doubt about safety procedures, consult with your supervisor. To test at a distance while maintaining excellent directionality for picking up ultrasound, we recommend use of the parabolic reflector, explained later in this program. The basic scanning method is used to locate the presence of electrical discharge. It can be used for virtually any area that can leak. Since anything can become damaged and therefore be a site for leakage, everything should be scanned. Here we are checking terminations, stress cones, potheads, and splices. First, using the ultraprobe scanning module, we'll follow the intensity of the signal to get closer to the site of electrical discharge. This is the first step of what we call the gross to fine method. To pick up gross signals, scan with the sensitivity level set for most situations at maximum, or 10. Use the fixed band mode. The meter mode should be in the log position. Scan the area, closing in on the leak site by listening for its characteristic buzzing or frying sound. Next, use the rubber probe to narrow the field to get closer to the leak site. But always respect the power of electricity. Don't get too close. Then reduce the sensitivity to pick up the fine ultrasonic signals and listen. Follow the ultraprobe by watching the meter and listening for the loudest point. Once the leak has been located, confirm the site by moving the probe back and forth in all directions, maintaining a safe distance. You will note that the sound level increases as you pass over the leak site. These steps are all you'll need to locate most electrical discharge. At this point, you may investigate further using other complementary technologies. For some situations, more advanced ultraprobe techniques are required. For testing high-voltage equipment at a safe distance, for example, the parabolic reflector is used. The standard ultraprobe scanner, the patented trisonic scanning module, has 3 transducers, and its field of detection tends to widen with distance. The parabolic reflector has 7 transducers, making it a powerful add-on for special purpose and long-range testing. It has a very tight, narrow band of detection, making it extremely directional. Its special shape and sighting mechanism enables users to locate an exact trouble spot at distances exceeding 200 yards. Another testing situation which may require advanced techniques is a noisy environment. In certain plants, when working with mid and low voltage equipment, for example, you may need to avoid potentially confusing stray sounds. This may be as simple as shutting a door. When possible, it is best to turn off the source of competing ultrasound. However, it may be difficult or impractical to turn off competing sounds. In these situations, various shielding techniques can be used effectively to block out competing signals. First, try the rubber probe to deflect the unwanted sounds. Changing the angle of the ultraprobe may also help. You can use your body to block out some kinds of competing sounds. Changing the frequency to around 40 kilohertz may help in some situations. Draping a welder's curtain or drop cloth may also help. Ultrasound works well when used in conjunction with other technologies, especially with infrared testing. As one ultraprobe user explained, infrared inspections allow operators to see light the eye cannot see, and ultrasound allows them to hear sounds the ear cannot hear. This is particularly important where surface temperatures may mask infrared detection of an underlying problem. Sound waves pass through any tiny crevice and are readily picked up with the ultraprobe. A switchgear enclosure can be tested using ultrasound without opening the door and shutting down power. By scanning around the seal of the door, sounds of discharge can be detected. Arcing, tracking, and corona may be present without creating hotspots that can be detected by infrared testing. When these conditions exist, there is potential for failure. Immediate action can avert disaster. The ultraprobe expands your field of view and readily identifies these dangerous conditions. There are new applications and techniques devised for the ultraprobe all the time. Although the majority of the applications are for high voltage, there may be situations where it is appropriate to check low and medium voltage equipment, such as connectors, relays and contactors, splices, and occasionally circuit breakers where there may be loose wires or breakers. The ultraprobe may be used effectively in conjunction with other low voltage testing methods because of its ability to pinpoint the exact location of a problem. In low or mid voltage environments, the sounds of electrical discharge will have less intensity. Judgments must be made based on comparisons with other normally operating equipment. The difference between a problem and normal equipment may simply be the difference between a small sound and silence. Because the difference between low, mid, and high voltage testing is one of magnitude, establishing a baseline for comparisons is essential to identify a worsening condition, especially at lower voltages where sounds may be less obvious.